In this video, we solve problem 9.8.070 from Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. The question says, or the problem statement says, the series represents a well-known function. Use a computer algebra system to graph the partial sum s sub 10 and identify the function from the graph. So notice, first of all, that s sub 10 actually doesn't correspond to an exponent of 10 here. When n is equal to 10, we're going to go, this is going to be x to the 2 times 10 plus 1, so it's going to be x to the 21st. So I just want to expand this a little bit so that we know what we're graphing, and then we'll graph it. So we have the sum as n starts, or as n goes from 0 to infinity, so we start at 0, of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. First, let's write out the 0 term, the n equals 0 term. When n equals 0, we've got negative 1 to the 0 times x to the 2 times 0 plus 1 over 2 times 0 plus 1 factorial. So that's a negative 1 to the 0, which is 1. That's 2, or x to the 2 times 0, which is 0. 0 plus 1 is 1. So this is an x to the first over 1 factorial. So that just ends up being an x. And then when n equals 1, we get this. We get negative 1 to the n, x to the 2 times n plus 1 over 2 times n plus 1 factorial. But this time our n is equal to 1. So this ends up being a negative 1 to the first. So that changes from positive over here to negative over here. So this guy is just going to flip back and forth from negative to positive. When n is even, we'll get a positive number. This negative 1 to an even power is positive 1. When n is odd, we're going to get a negative number. So the terms are going to flip back and forth from positive to negative, positive to negative. This is an alternating series. So I've got negative 1 times, and that's x cubed. 2 plus 1 is 3. So I think I'll just write it this way. Negative x cubed over 2 times 1 plus 1, that's 3. Again, factorial. I hope you see the pattern. We're going to flip back and forth from positive to negative to positive to negative. 2n plus 1 is always going to be an odd number. So when n equals 0, we get 1. When n equals 1, we get 3. When n equals 2, we get 5, and so on. And then this factorial in the denominator is the same number as we have in the exponent here. So when that's 3 factorial. When n equals 2 and that's 5, that's going to be 5 factorial. So if the pattern continues, what we end up with is plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And they ask for the 10th partial sum. So you just keep going until this is x to the 21st. You might say, oh, that's a lot, but the pattern is so easy to see that it's actually not that difficult to write all of the terms out all the way up to x to the 21st. And I've even run out of space. Plus x to the 21st over 21 factorial. And then the next term would be negative x to the 23rd over 23 factorial, and we keep going. But s sub 10 is this guy. S sub 1 is this one. S sub 2 is the sum of those two. S sub 3 is that, and so on. So we just need to find a calculator for this, go to Grapher online and then graph this, and then we'll see what this function looks like. I'm going to use Desmos.com. So I'm over here in Desmos, and I'm just going to graph capital S sub 1 of x, and I'm going to call that x. And then I'll say s sub 2 of x is x minus x cubed over 3 factorial. And s sub 3 is just like that. Now you could write out those first two terms again, but I think what I'm going to do is I'm going to define this in terms of the last one. So I'll say s sub 3 is s sub 2 plus one extra term. It's going to be the x to the 5th over 5 factorial. And then you can keep going. S sub 4 is that last partial sum plus the next term, which is negative x to the 7th over 7 factorial. S sub 5 gives us this, s sub 4 plus x to the 9th over 9 factorial. And they wanted us to go all the way up to s to the 10th. So we could type out all of these this way, but it might just be easier to type all s to the 10th immediately. So s to the 10th is going to be s sub 5, minus this x to the 11th over 11 factorial and so on. So I'll just type that in. So you could have just gone straight for this if you wanted to. I wanted you to see the partial sums though. I wanted you to see more than one. Okay. So let's turn off all these other graphs for right now and just look at s sub 10. Question is, do you recognize that? What graph does it appear to be approaching? Well, let's start at the beginning. There's s sub 1. First partial sum is just x. Then we've got a cubic polynomial. And you've got this 5th degree polynomial in green, 7th degree polynomial, 9th degree polynomial. And you keep going, and I chose not to graph s sub 6, s sub 7, s sub 8, s sub 9. But do you see what it's approaching? You see that sine wave? Turns out if you take infinitely many terms, you get sine of x. So I'm going to graph f of x equals sine of x. Look at that. So there's the sine function, and there's the 10th partial sum. It's indistinguishable from the sine function between, it looks like negative 8 and 8 approximately. And then just after 8, when we go just beyond 8 over here, or just beyond negative 8 over here, the partial sums, that 21st degree polynomial, starts to deviate from that sine function quite a bit. So yeah, that's all you do. The question asked us to identify the function from the graph. When we look at that, we saw that it looked like a sine function. And I would just use a program like Desmos.com or a website like Desmos.com to prove to yourself that that is what that's equal to.